Hello there. In this video I'm going to discuss an LC circuit, that is a circuit made of an inductor and a capacitor. We're going to start with the switch open and the capacitor fully charged. So the current in the circuit is going to be 0 and capacitor charge is as you can see in the picture. So at t equals 0 we close the switch, and so what is that? At that moment the current is going to start flowing out of the capacitor, discharging the capacitor. So the sum of the potential differences along the circuit we know it should be equal to 0. The potential difference across the capacitor, if we move in the counterclockwise direction, would be positive, and it would be Q divided by C. And the difference in potential through the inductor would be minus L di dt. Notice that the signs are as indicated in the picture, because di dt is going to start increasing. The current is going to start increasing from 0 to some value later on. So di dt is positive, and because of that the inductor is going to try to resist that change in current, and the way to do that is to have a potential higher at the top of the inductor and at the bottom. So the signs for the inductor are as you can see in the picture, and when we move counterclockwise in the circuit, the difference in potential of the inductor is going to end up being negative. So the sign minus L di dt makes sense, and the sum of those differences in potential are equal to 0. Moving L di dt to the other side, we get this. That's a differential equation. There's one more step that we have to do to be able to solve it, which is that the current that is flowing out of the capacitor is discharging the capacitor. So we have that the dq dt is negative, and since we assume that the direction of the current is positive as indicated, we must have a negative sign in front of it to indicate that it's a current due to the discharge of the capacitor. So I should be equal to minus dq dt. We take one more derivative to that equation to get di dt is equal to minus second derivative of q with respect to time. And now we can replace in the right hand side of that equation the equation that we started with. So the left hand side is still the same, q divided by c, but now in the right hand side we can replace di dt with minus second derivative of q with respect to time. So this equation, let's flip the sign to the other side, looks exactly like the equation for a spring mass system. Remember that for a spring mass system the force of the spring is minus kx. The only force acting on the system equals mass times acceleration. So notice that the structure of these equations is exactly the same. So since we already know what the solution for the position as a function of time is for a spring mass system, and we know that that solution is periodic, and that the angular frequency is the square root of k over m, that tells us that for our new equation here for the LC circuit, the charge in the capacitor should also change periodically with time, q0 cosine omega t. And we also know that the angular frequency is going to be the square root of the number multiplying q, in this case 1 over c, divided by the number multiplying the second derivative, which is L. So we get that the angular frequency of this circuit is going to be the square root of 1 over LC. Knowing that the charge is cosine of omega t, that gives us the current as the negative of the charge with respect to time. So we get that the current goes like the sine of omega t. q0, omega comes out of the internal derivative of the omega t term, and we get q0 omega sine omega t. So basically the charge, it's a cosine function for the situation that we set up as a t equals 0 closing the switch, and the current behaves as a sine function. So notice that when the current reaches a maximum, the current is 0. When the current is a maximum, then the charge is 0, etc. So this oscillation happens with a periodicity of 2 pi over omega, as you know, and given that omega is the square root of 1 over LC, we get that the period of this oscillation is 2 pi square root of LC. So surprisingly, in this kind of circuit, the current and the charge continues to oscillate back and forth forever. If there is no dissipation, there is no resistance in the circuit, the oscillation goes on forever with the current and the charge going back and forth. Notice that in this that the role of the inductor of the capacitor is similar to the role of a spring in a spring mass system, and that the role of the inductor is similar to the mass of the spring mass system. The inductor plays the inertial part, that is, the mass has inertia. The inductor also has inertia, in the sense that it wants to keep the current at a constant value. So, because of these oscillations that we just discussed, the energy is going to be moving or becoming or converting from one form, electrostatic energy, into magnetic energy, back and forth, with the total energy obviously constant, but the energy becoming one, fluctuating between one form and the other. That's for example, when the charge in the capacitor is maximum, we know that the current is zero, so that means that all our energy is electrostatic. But later on, the current is going to become a maximum, and the charge in the capacitor is going to be zero. So that means that the inductor is the one that is going to be keeping all the energy of the system. It's going to be electrostatic, electromagnetic energy. That would be in this picture, what I'm illustrating in this picture. All the energy in this case is electrostatic, and in this picture, when it's quarter of a period later, when the current in the inductor is the maximum, we have all the energy in the form of magnetic energy. Notice that this was exactly the same situation with the mass spring system. When at t equals 0, when we release the mass, all the energy is in the form of electrostatic, elastic potential energy, and a quarter of a period later, when the mass is going through the equilibrium position, the energy is all kinetic. Alright, this is all I wanted to discuss regarding this circuit. I'll see you in the next video.